the bottom. No, yours.
Yes,
No, so we unmuted it.
it's unmuted.
Yeah, he's fine. Go ahead.
Okay, so the main goal for our project is to provide clean and safe water for disaster relief, and in order to do that, we wanted to start by actually thinking about the location. Because in this case, the location is very important for us for logistic and cost aspect. And we know, like most of the wildfires happen in the eastern side of the United States, and we wanted, when we were looking for a location, we wanted to choose a location that's close to a lot of wildfires, and also surrounded by many water resources like lakes and whatnot. Also, it was important to consider a place that gets a reasonable amount of sunlight. And for our location, for the distribution point and for the distribution point, we chose Sacramento, California. Why? Because California gets, in 2020, actually, they had more than 10,000 wildfires, depending on the size of them. And it also, as we can see here in the temperature scale, in July it gets to average of 35 degrees. So that's ideal for our system, and it also gets a 15 hours of sunlight. And you can see here it's surrounded by many sources. This actually was taken this week, so I just speak some of the websites that are set on. So it's the winter. We have different places to reduce the shipping cost. We can also use the distribution point to supply other states as well with the products. And this again can reduce the cost of the shipping and can provide fast and easy access. And for some of the cost estimates, so we have fixed costs. So these are initial values, but for let's start actually with the variables. The variable costs, we have the operations like salaries and like renting warehouse and stuff. We have customer service, marketing, and shipment. Shipment actually depends on like weight and distances and partnership contracts and like many other factors. And for the fixed ones, we chose 10 pipes for the thermal modules, and most of the cost goes into manufacturing the tubing system for the two modules, the thermal and the UV. We found that there is actually a module that has the glass included already in the. So if we see here, this is the outside of them we have the glass ones, as we explained in the previous presentation. For the thermal modules, we have the values of 20 to 30, depending on the sizes, but we chose to go with 0.5 meters for this application, and the storage tank is between 15 and 20 for actually more than what we need. We need like around 14 liters for our application, and this provides us with 20 liters. And one more thing to consider is that we think that we will have more clear projections once we are finished with the business canvas. It just gives us like a clear idea of like partnerships and customer segments. And also, as you, Professor, mentioned last presentation, costs in this application and in this case during disaster relief, it's not, cost is important, but in this case, it's not as important as efficiency and functionality. And for our calculations, we did some calculations on different aspects to understand of how the system would work, and we did it on the solar radiance and the fluid flow, the heat transfer, and the pre-treatment tank heating. And Jared and Andrew will go over the calculations.
Okay, so in order to actually heat up water, you need solar irradiance. But solar irradiance is not constant, it's variable. It depends on not only the season, but also your location on Earth and the sun's relative position to that. So Sandia National Labs has big interest in actually looking at how efficient solar modules can be. So they developed this large library for calculating their efficiency. But I was interested mostly in one small part of it that deals with the sun's location. So after just taking that specific module and doing some modifications, we can get the solar irradiance on any location on Earth at over any time span. And so what we're seeing here is the solar irradiance is a function of time on a clear sky day over July, August, and September. We chose those months because those are the worst months for fires in California and the times when we're most likely to have a disaster. What we found from this is that we actually have a somewhat big problem. There's really only a short amount of time that we can actually have full irradiance from the sun. And as we go towards September, when things dry out, our problem actually gets worse. So making the assumption that we have constant full irradiance simply isn't going to work. We have to account for this. A number of assumptions we're making here that we're using a San Francisco location. We can move it if we need to, but for these calculations, that's what we chose as the latitude and longitude. And then we are neglecting the effect of humidity on solar radiance, but it would probably make things even worse. Okay, so the next thing we looked at is, right, that previous plot was just looking at global horizontal illumination, which is just if you have a flat plane on Earth, right? But most solar panels are tilted for a reason, and that's because that tilt affects the performance, and depending on the sun's location, that also has an effect. So I decided to look at what the differences in terms of efficiency and radiance would be, depending on what our tilt would be. So if we look at this in July, there's actually a very negligible difference in terms of the radiation that we get, depending on whatever angle we have. Even if we added a horizontal angle, we'd still do okay. But when we go to September, when the sun's angle to the Earth changes, we actually get significantly varied results. And it turns out that we actually really want to optimize the angle at which we're having our device oriented towards the sun. This is also assuming that it's oriented towards the south relative to north. So this ends up being a huge consideration in terms of our calculations and the design of our system overall. All right, Jared, take it away.
The fluid flow calculations are all based on the geometry of our box and the pipe size. So some assumptions I have is I'm not accounting for friction of the water or the water changing temperature and changing how well it flows due to temperature. That was too detailed for this part of the calculation. I also assumed water dynamic viscosity was constant, but in reality it changes over temperature, and that got very complicated quickly. So we assumed this value for this calculation. And then we did all these calculations separately. And so for me, I assumed the pipe diameter was 5 centimeters and the spacing, meaning spacing between the pipe and the wall of the box and the pipes from each other is 1 centimeters. And I use that to calculate things like how many rows of pipes would fit, and how long is this path of water. So in my plot, you can see the UV time in blue, and I have the flow rate in kilograms per second on the right, and water velocity on the bottom. The conclusion I got from this is that making the box bigger didn't change a whole lot. You can see the thinly dotted lines don't give a whole lot more of UV time, but slowing the water down affects it a whole lot more. So if we can have the water have an average velocity of something very slow, definitely less than 1 meter per second, that's going to increase the UV time the most. Can you go to the next slide? Thanks. The other calculation I did with the box is the trough, the parabolic trough mirrors that lie underneath the tubes. The picture in the bottom right shows kind of a cross section of this where we have a parabola mirror. And the thing about parabola mirrors is that they have a single focal point. Circular mirrors have like an area, focal area. They aren't all constant. So for these calculations, I'm just assuming a parabola. I'm also ignoring the shadow from the pipe, which we'll want to account for later. I'm assuming, just for the sake of cleanness of plots, 1 meter by 2 meter box size, and again, a pipe diameter of 5 centimeters. And I calculate these. Okay, I should explain this. The mirror width is the length of the aperture, meaning the opening of the mirror. And the mirror length is how long the mirror goes from side to side in the box. So it's the trough length. And then the depth is how deep the mirror is. And I calculate the width and length based off the box dimensions and the pipe size, just to automate some things, reduce the parameters we're changing. But I did change the depth to kind of help us see where the focal point would be, and what our concentration ratio was. And I found that the box dimensions had a really minimal effect on it. The mirror depth had a lot greater effect, and the spacing of pipes from each other had a lot more effect of how much the concentration ratio is. And that's what we're trying to maximize here. Do you want to go to the next slide? Thanks. These are my calculations. The quick equations I had. The one I wanted to focus on most was the concentration ratio. It's aperture area, meaning how much sunlight goes into that parabola mirror, divided by the pipe area. So it's how much sun are we concentrating down into a smaller area. And as you can see, a 1-to-1 ratio is like the worst we're going to get. And that very bottom dotted orange line you can hardly see isn't great. It has a spacing of the pipes are half a centimeter far from each other. So of course, not much sunlight is going to get to these mirrors. So yeah, increasing that spacing is really going to increase the concentration ratio a lot. And we just want to play around with what spacing we have, along with the previous slide I showed with how much UV time we can have, maximizing the length of the pipe. Thanks.
Can I jump to just the plots then? Okay, I won't explain how I did all the calculations, but essentially we have our optical efficiency, and then we have our heat coming in from our solar radiation, and then that is balanced by the useful heat that is transferred to the water and the loss that is evaporated or convected or radiated away. So what we, and then eventually it conducts, and it's based on Nusselt's number and fluid flow properties, area and whatnot. But if we look at different tube diameters and the velocity that's flowing through them, we can start to calculate different heating rates. So what we see is that ideally we actually want to increase the diameter of our pipe, and we want to slow this down as much as possible, which is also a similar conclusion to what Jared found. Now, if we have a situation where we stop the water and prevent it from flowing through to the next chamber and just let it sit there until it reaches a temperature, we can actually also see a time in seconds to the 65 degrees Celsius critical temperature as well. And in the same sense, we also see that having bigger pipes ends up being beneficial for this as well. A lot of this comes down to the different fluid flow properties. Yeah, and a lot of that has to do with heat losses as well, and absorbed energy. So we weren't able to actually get the pre-treatment calculations done, but I took experimental data. And the most important thing is that over time, over the span of days, we can actually continuously increase the internal temperature of this chamber that's holding the water. So when we start to consider how this, in terms of a long-term application, we get added benefit the longer it's in operation. And I ended up doing some fitting of lines and did some extrapolation. If we do have constant irradiation, within a single day, we can get up to 70 degrees Celsius as the internal temperature, and we only lose temperature at night at a rate of half a degree per hour. So we really stand to benefit here. And well, I guess open up the questions. Sorry, we had to rush through that. Okay, absolutely.